lab session, of course. Is it visible to all of you?
Yes, sir.
Sorry,
Yes, sir.
is it visible? Okay. So today's motor characteristics. So we are going to learn what is DC servomotor, why it is called servomotor, and how shall we determine the characteristics and how the characteristics look like, all aspects of DC servomotor. The first thing, why DC servomotor is so important for control system engineering. You can say actuator or final control element. Most of the control systems in industrial settings are primarily servo control system or tracking control system, you can say. Tracking control system are also called servo control system. The name servo originated from the word servant. That means they are slave. What you command, the servo motor will follow that, will do all the necessary work and follow your command. Primary objective is to track the reference input, and the type of the system, control system, is electromechanical in nature. Invariably, you will find DC servo motor as the actuator or final control element. So points of discussion are what is servo system, significant aspects of DC servo motor, and necessity of this experiment, experimental setup, procedure, and some sample data. So in an example of servo system, servo mechanism, also called servo mechanism, where a mechanism, of course, it's an electromechanical system, where the feedback control system is utilized, in which the control variable, that means the position, the speed, acceleration, etc., electromechanical system or mechanical system. Okay, so there you give a position by means of some analog signal or by computer in the form of digital signal, reference signal. It goes to position control unit. Then there is a servo drive. The control unit generates necessary control signal to drive the servo system. Okay. Servo drive is basically an amplifier or power, you can say power amplifier, which amplifies the control input or control signal generated by the control system. Okay, because the signal output from the controller is very weak. It's just a signal, not a power, but it has necessary information how to control. So it has to be amplified by a driver or amplifier, and that special name for that driver is called servo drive or servo amplifier. We will see it later. And that provides necessary power to the motor, and motor runs. And if torque has to be amplified, then we need a gear train to manipulate the torque, increase or decrease, whatever. So speed and torque matching, you can say, is performed with normally the motors run at high high speed, low torque. So, but the mechanical systems require high torque, and they invariably run at low speed. So you need a gearing arrangement. Reduce the speed, so the torque for constant power, the torque will increase. And it's very simple schematic diagram is shown regarding this mechanism. And motion variables like velocity, acceleration, displacement are being controlled in a closed loop, and its position is being sensed. A good example is a CNC machine, computer based CNC machine, computer where the computer control is performed. Okay, computer numerical control, CNC. Now the simplified block diagram looks like this. You are very much familiar with this type of block diagram. So reference input, there is a feedback loop which senses the actual position or actual variable. We detect it, we apply it to amplifier. Then where is the controller? Actually, controller is there inbuilt. Here we are using proportional control is always there in the form of unity gain. So in this type of you are comparing PID controller is error. You have already studied. So error into unity gain. So that is virtually, you can say, one control input, and that is amplified by an amplifier, and the servo motor takes that input in armature control mode or field control mode, whatever. So, and the control action is taking place. So servo motors, feedback control system, or servo motor has been taken from the very হ্যালো, হ্যাঁ বলছি। একটু 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 হোল্ড করুন, আমি একটা okay. Am I audible now?
Yes, sir.
Okay. So this diagram at the bottom, you can see this device. So this is not unknown to you. Two potentiometers, when we connect two potentiometers in this configuration, and you know this configuration is called error detector. When two identical potentiometers are connected back to back, okay, I can assign one potentiometer as a reference position to indicate its reference position, its wiper, that means variable point. If I go on moving the variable position of the other potentiometer, what happens? and error voltage is being generated between this point and this point. That means across the variable points, isn't it? Also, I can use this feature of this error detector as as position error. So say the input position of this potentiometer is kept as reference position, angular position of the motor, say. And I have coupled the output shaft with this potentiometer. Motor of the motor shaft, what will happen? This all input port. What will happen? The angle of this motor will be sensed. Now, if the input potentiometer angle setting and output port angle becomes same, what will happen? The error generated will be 0. If to the armature of the motor and it takes corrective action. So this is harmonic motor in position control mode. This experiment will be performed in the next year. Now, this diagram actually an exaggeration of this diagram and quite familiar to you. I'm skipping it. Yeah, the construction of DC servo motor. There are two coils. One is armature coil and another one is field coil. The DC servo motor of so what happens? আর কোনো ফোন ধরবো না, বিরক্তিকর. Let me keep it in silent mode. Yeah, no more disturbance. So there are two coils. The construction wise apparently looks same. The two coils, armature, commutator, everything. The adjective prefix servo appears. Actually, it has a significance. Construction wise, apparently it may look same, but there is a difference between the ordinary servo motor and DC servo motor. Ordinary DC motor and DC servo motor. Then what we want, an actuator, the desired characteristics of an actuator is that it will be fast. Its response will be fast. That means its dynamic characteristics should attain. It will exhibit some dynamic characteristics so that it's a steady state. Its steady state is attained in minimum time. So in order to achieve that, what you need you have to achieve very small time constant of the system. Every large, whatever. Aspects in system theory, you might remember that DC servo motor has two time constants. One is mechanical time constant, another one is electrical time constant. Now, electrical time constant is quite small. Servo motor as a first order system. So, two time constant means second order system. There will be two poles, but we neglected one pole because of the L by R ratio, which is very small. Now, the mechanical time constant cannot be neglected because it is significant. Now, in order to reduce the mechanical time constant, what should be done? So, we have to look into the mechanical design in that case. The mechanical design of any rotating machine says that the power, mechanical output of any rotating mechanical machine is proportional to the square of its diameter and proportional to its length. Now, in order to reduce the element in mechanical time constant is its inertia, moment of inertia. Okay, so moment of inertia again is proportional to its diameter. So if I reduce the diameter of the armature, which is the rotating part, what will happen? Its moment of inertia will be reduced. So its mechanical time constant will get reduced. But what will happen? If square of diameter, so its mechanical power output will get reduced, which we do not want. So in order to compensate, increase the armature length appropriately so that the total power output remains constant, or as we envisaged. So we can say that in a DC power, if there are two motors lying in front of you, one is DC servo motor and another one is just ordinary commercial DC motor, how will you identify the DC servo motor? Which one is DC servo motor? It's very simple. As I said, DC servo motor should have a small moment of inertia. So we have, by design, we have reduced its diameter and increased its length. So the motor, DC motor, which has longer configuration and longer and thinner configuration will be DC servo motor. Okay, of the same power rating. A DC motor, ordinary DC motor, and a DC servo motor. By comparing their size, their configuration, the longer one will be DC servo motor because it is designed in such a manner that mechanical construction is such that it has small moment of inertia. That is one aspect, the mechanical aspect. Now, from the electrical point of view, electrical characteristics point of view, we want the DC servo motor should have linear characteristics. The speed torque characteristics should be linear so that our closed loop operation, this operation, is not disturbed by the non-linearity, any type of non-linearity. You know that in a system, if any one non-linear element enters, then the entire system becomes non-linear. But controlling a non-linear system is a bit difficult than the linear system. I have not yet studied the non-linear control theory. There are possibilities, but that effort is very, very involved. Expertise, but if we can keep our systems, our components in a system linear one, then the control will be easy. So our effort will be during the design, electrical design, that the system electrically is a linear one. How to do that? Uh, there are two main aspects in a machine design. One is the coil, design of the coil. That means the electric circuit. Two magnets. Two magnets are basically interacting. Yeah, we can say that. Here in our, as I missed one point I missed in our the DC servo motor that is in our laboratory has permanent magnet field. So this field coil is not there. Instead of this field coil, we have a permanent magnet. Okay, so that is one modification, special case. Otherwise, you can make a coil for field, and that current will be fixed if I do not use field control. But if we have a this kind of design, that means separately excited, then we can control both field as well as speed, armature. But field control is very rare phenomena in induction motors, from the rated to the minimum possible. So field control is normally not carried out. So modern DC servo motors this field coil is replaced by permanent magnet, because high speed motors are nowadays available at a very low price, like BLDC motor, which can run at a very high speed, and size is also small. So we can see that very strong field magnets of very small volume are available nowadays. So our most of the DC servo motors are armature controlled DC servo motor. So in order to achieve linear design, what should be the main factor? Magnetic circuit. Because we know that the magnetic material, they show some non-linearities due to its hysteresis property. So during the magnetic circuit design, we should select the nominal value of field magnetic field strength. Okay, magnetic field strength, or you can say nominal value of flux density, rather nominal value of flux density, more specific from the design point of view, so that the variation in voltage, armature voltage, because armature voltage is proportional to flux. Okay, creation of flux is due to the armature voltage in the armature. So armature voltage, variation of the armature voltage does not force the operating point, actual operating point of the flux density to penetrate in the nonlinear region. Okay, so during the design, we will keep the nominal flux density. I hope you know the nominal flux density around which the variation will take place, maximum and minimum, so that this maximum variation in both sides, minimum side and maximum side, saturation. That is my point. Or should not cross the knee point in the magnetic characteristics, magnetization characteristics. So you have to keep the flux density in the design small. So a bit more magnetic material will be required. So from that perspective, you can say your DC servo motor may become a bit heavy because of the additional requirement of iron to keep it a linear one. Any doubt? Any doubt regarding this point? Okay. So I have already explained it. Dynamic response here. So I have already explained these 2 points. That is, we have to keep the inertia small, so its axial length should be large, and small diameter should be maintained. And we should keep the magnetic property linear. So for that, one aspect is if you use the commonly available magnetic material like CRGO, so your attempt should be to keep the flux density smaller. Otherwise, you can take good quality magnetic material, which allows very or not very but quite large flux density and a linear region. And apart from that, from the mechanical perspective, you should use good quality bearing so that they do not introduce non-linearities, because you know that gears, ordinary gears, they should. Bearings may also offer non-linearity because of friction. So this should be minimized so that you can get linear characteristics. How the linear characteristics will look, I will show some diagram later on. So for the time being, this point should be very clear to you. Now the experimental setup that we have in our laboratory, let me explain it. If you have chance to perform some offline experiment as students did in the last semester, you can get familiarized yourself with this experimental setup. So DC servo motor is here. If you open this cover, you can see the DC servo motor. It's just like a DC motor by appearance, but if you compare it with the same power rating of other motors, commercially available motors, you will definitely make that difference by yourself. And the shaft is connected with a disc, metal disc, aluminum disc, and its purpose I'll explain. And the shaft is coupled by a flexible coupling with the tacho generator. Its output voltage depends on the speed of the incoming shaft. So misalignment. So in order to avoid the result of misalignment of two rotating shafts. So if any misalignment occurs, what will happen? There will be unbalanced force or unbalanced torque generated, and that will damage the bearing. So a flexible shaft coupling is applied that will absorb the sensor, because disturbances. The tacho generator output is used for feedback in speed control. Now here we have an arrangement of applying load, mechanical load. So we have taken a very simple arrangement. A very powerful permanent magnet brake is there. So there are two magnets, U-shaped magnets, and they are side by side and maintaining opposite polarity. So here if it is N, here it will be S, and other side also like that. So a continuous magnetic field will be flowing, flux lines, complete the path through this two U-shaped magnets. And in this air gap, I can move this pair of magnets in this way and that way, so that what will happen if I move the magnet towards the shaft, what will happen? The disc, which is coupled on the rotating shaft, will cut the magnetic flux. And if there is a flux cutting, what will happen? As it is an aluminum disc, eddy current will start flowing through it. So it will oppose the cause. That means the interaction with the magnetic field. So what will happen? A torque interaction is due to this rotation of the disc. So there will be opposite torque will be developed to obstruct the motion. Okay. So that is actually the mechanical load, we can say, being applied on the shaft. So we are basically applying the mechanical load on the shaft by virtue of this AD current break. It is current break. And as I explained earlier, in position control mode, what we do, we take one input potentiometer and another output potentiometer. The output potentiometer is coupled to the shaft by some reduction gear arrangement over here. And here it is also calibrated over here. You can see the reading. And this block is the upper panel where you can get the terminals. Here also upper panel, here you can get the terminals. Basically, operational amplifier based signal comparator. Signal can be fed over here, the feedback can be fed over here, and it will compare it, and error will be produced. And it's the PID controller, and this is one. This is another potentiometer, rotary potentiometer. This is a PID controller. Now, this is a servo amplifier. What is going on? এই যে আলামিন ইসলাম, তুমি এতক্ষণ কোথায় ছিলে বাবা? আধ ঘন্টার উপরে হয়ে গেছে, ক্লাস নিচ্ছি। তোমার জন্য আর কিছু রিপিট করা যাবে না, অন্যদের থেকে জেনে নিও।
ওকে স্যার, থ্যাংক ইউ।
এরা কোথায় থাকে? বিনয় কুমার রজক। এত ক্যাজুয়াল হলে হবে না, শেখা যাবে না। থার্ড ইয়ার সেকেন্ড সেম, এখন এরকম কেন? পিছিয়ে পড়বে। পিছিয়ে তো পড়েছো তোমরা, মনে মার্কস টাক্স ওঠে না। তার কারণ হচ্ছে তোমাদের ইয়ে নেই, মানে কি বলে, ইন্টারেস্টটাই গ্রো করছে না। নিজেকে ইয়ে করতে হবে, মডিফাই করতে হবে। এরকম করলে চলবে না বাবা। মাঝখানে গিয়ে টুংটাং করে আওয়াজ হয়, ইন্টারাপ্ট, এগুলোতে আমার অসুবিধা হয় পড়াতে। যাই হোক, কিছু করার নেই। ভাবনা চিন্তা করে বলছি জিনিসগুলো। Now let us come back to this block, servo amplifier. As I said earlier, the signal. So here we are getting signal, here we are getting signal, here also signal. Tacho generator, the sensor also gives a signal. Okay, but the signals cannot be fed. The controller, again controller ta nei. It's a PID controller. So controller also gives signal. Signal cannot drive a motor. It does not have necessary power because it is exclusively designed and fabricated for feeding servo motors. Why exclusively designed for servo motors? Because its characteristics is kept linear. Is audio amplifiers. Why nearest neighbor? Because the frequency band of any control system equipment is audio frequency range. If any device can work with audio frequency, that device can also work for control system. That is from the perspective of engineering. Find many audio amplifiers of very high power rating. So you can, if you get a substantial power out of a audio amplifier, that can also be used as servo amplifier, because audio amplifiers are very linear amplifier, very precision and linear amplifier. This servo amplifier also a kind of very precision linear amplifier with audio frequency bandwidth, because the frequencies of interest in control system lies within audio frequency. almost always. From 0 to some 20 kilohertz or so. Select some non-linear amplifier, what will happen? The control signal that is generated over here, its waveform will get distorted. If its waveform gets distorted, what will happen? The command that will appear at the input to the actuator will not be proper control command, and the actuator will also malfunction, and the feedback control action will not be successful. That's why the servo amplifier should be very, very linear amplifier, or the operating point and the allowable area of variation around the operating point should be quite large. Very large linear region should be there. That's why it's costly. Servo amplifiers, audio amplifiers, they are very costly. That's why. Because precision components are required to achieve this type of amplifiers, as well as their power carrying capacity is more. That's why you require elaborate cooling arrangement, and their size is bigger, because the power loss through the servo amplifier and audio amplifiers are power loss due to conduction mode of a transistor or MOSFET, whatever, average current. And that is quite high. Anyway, supply is there because you need power supply for servo amplifier, power supply for all other equipments, like in the potentiometer, you need power supply. Okay. Taco generator. So servo amplifiers are basically one, you can say, valve. It is controlling according to some signal being provided by the supply. So power supply is giving power to the DC servo motor through this servo amplifier. It's like a valve, you can say. And the opening and closing of the valve, you can say, is being carried out by the controller as per the control system, arrangement of the control system. They are just modulating the power. All the signals and systems necessary to modulate the power is the subject of the design of control system. So this is connected, this side also ground, this side also ground. That is not the case. There is a jumper over here, and this is connected between this point and this point. So this is actually eddy current brake unit, and this is taco generator, and the field coils are no more there. So it's actually a very old diagram. Earlier, about 20 years back, the setup was separately excited, but that has been replaced by the new one. New one has separately permanent magnetic excitation. No. This is actually armature coil. Actually, this diagram again wrong. The armature coil configuration is not like this. So we will carry out necessary modification in the next revision. This is not the proper drawing. So anyway, let us think it as a black box. It is a servo amplifier. Whatever signal is appearing over here, it is being amplified and being fed to the armature of the DC servo motor. That is the actual case. Perform this part of the experiment. What is given? A characteristic is given. Brake torque characteristics has been represented here as brake position. There are a few brake positions like 2, 3, 4, 5, up to 10, and the torque, mechanical torque applied by the brakes in this position are like this test was carried out at 1000 rpm, and that time the tacho generator constant was 2.7 volt per 1000 rpm. So tacho generator is a linear device, so as per if the speed becomes 500 rpm, so that will give you a voltage of 2.7 by 2, like that. In the brake position, regarding the brake position also, for brake position 2, if the speed is 1000 rpm, the torque will be 5 millinewton meter. If the speed is 500 rpm, then the torque will be just half, like that. For all other positions, you can also calculate the mechanical torque in this manner. Now let me show you some demonstration video. Here the picture will be more clear. Yeah. Zoom has been carried out. So this is the comparator, as I said. So I'm moving this. Let me show you. Yes, this is movable. The brake is movable. So these are the positions, brake positions. See, this protruded shaft actually is required for position control. This shaft is coupled to the output potentiometer when we perform the position control experiment. Yeah, I tried to show you, but it's the darkness, because of darkness, not easy to follow, and it was not possible to remove the cover that time. So what we did here was an ammeter. In this power supply, there was an ammeter, but the ammeter resolution, the scale resolution was but crude. We could not make discrimination in low current variation setting. So we replaced or bypassed this ammeter by modifying the connections and connected one standard multimeter. With the help of the multimeter, we could take better reading of the armature current. Oh, this already. This part already. Oh, it is running. We will give supply. We'll give some reference input, and the rotation will start. Just start. It is just started rotating. The armature current, and now it is I think very small load has been applied. Very small load. Yeah, almost no load. I think brake position 2. So for that condition, armature current is this much. And I think this is tacho generator voltage or what? This is tacho generator voltage. Well, let me. So in this, let me show you step by step diagram. So what is the task during the experiment? I'll come back to the video once again. You have to change the input, reference input. reference input 1 volt first of all, then 2 volt, and set the brake at 10, highest brake position, and then go on reducing the brake position. And you note down armature current, the tacho generator voltage, and you have to calculate speed in RPM and speed in radian per second and torque. From this corresponding to the speed and brake position, you have to calculate the torque generated by the motor as per the diagram, table, load torque table, being balanced by the electrical torque generated by the motor. Otherwise, stability cannot be achieved. So from the stability, concept of stability, at the stable condition, the load torque and the armature generated torque, they are same, so that the steady speed has been achieved. So this will be carried out at input voltage, reference input voltage 1 volt and reference input voltage 2 volt. Then in the we have to plot the speed torque characteristics for different armature voltages. For different armature, we can calculate armature voltage also. This one. Okay. Now it's position 5, some intermediate reading. So voltage you have to change to required voltage, reference voltage. This is TACO, I think. And voltage not yet started. Where is the audio? So this is current reading. This is, I think, armature voltage reading. And oh my God, I cannot remember right now. And audio is not coming. Difficult. So 3 multimeters were there. And this is TACO. Okay. And if you calculate this data and if you calculate the speed and corresponding to VG, that means TACO generated voltage, and torque from the table, as I said, you'll get this type of characteristics for some input voltage and some other input voltage. So they are linear, but we want, in ideal case, they are to be parallel. But some mismatch is there. Okay, some because of some experimental error or some other because of some other reason. Sometime back it was performed, so I took a snap of that page to show you how the characteristics should be there. So individual characteristics are almost linear, but transition from one to another, there is some non-linearity, I can say. Now, let us see this video. Almost same video. In the next reading, what we did, we were curious to see the current variation. Okay, so what we did, we go on increasing the current from the minimum armature current to the maximum, say 1.5 ampere, and then we reduced. This experiment should be performed continuously. You cannot give a break. When the motor starts rotating, and from maximum, because of the heating, etc., and saturation consideration, that is the maximum current, and then you go on decreasing it gradually, and note down the speed as well as the armature voltage. Sorry, EI, input voltage, reference input voltage for that. So actually we are changing EI and current is changing accordingly, but we will go on changing because all the experiments are being performed in open loop. We are not performing this experiment in closed loop. So in open loop, input voltage, we have to vary it, look into the meter, ammeter, multimeter that is measuring the current, or ammeter, and see the current variation, and then stop and note down this value, and this value. These three readings should be taken: input voltage, reference input voltage, current, and tacho generator. In all cases, but in different fashion. So what is the use of this part? What is the use of this part? Yeah, that I'm going to tell you now. Yeah, if you plot it increasing and decreasing, then in ideal case, they should coincide. Here, they have almost coincident characteristics, but at higher value of input voltage, there is a bit mismatch. So they are very good. The servo motor is quite good servo motor. Its hysteresis is very minimum, very small. Its hysteresis is very small. Hysteresis characteristics is very small. Only there is a bit carved nature in the characteristics. That's why the earlier mismatch occurred. This parallel, these characteristics actually shifted from this perfect parallel location. Okay, because of this hysteresis, we can assess the nonlinearity from this experiment. Now, time response. Another one is dynamic response. You know this second order system, how does it respond for under damped system? So we want to characterize the so if you have any device to note down its step response, we could capture this step response with the device called strip chart recorder. This is a typical reading of a step response from the strip chart recorder of the servo motor. So here this time response is very similar to the time response of a first order system. Step response of a first order system. As we have neglected in practical case, as we have neglected is quite you can say correct over here. It looks very similar to first order response. So from here we can calculate various time, rise time, settling time, percent, no percent overshoot, 0. So all the time domain characteristics of a second order system which are relevant for this dynamic response can be calculated from here. One very important characteristics that we can evaluate from here is a model, mathematical model of the system. If I motor from these characteristics, how? If we neglect the electrical time constant, then we can approximate it as a first order system. Now from here, if I approximate it as a first order system, now from here I can calculate the initial setting as this point, and 2% rise of 63.2%, and I can count the time from here. So this is actually the time constant from the definition of time constant. Time takes to rise this much percent of the final value. Okay, so if I can find out the approximate time constant from this response, I can easily calculate the transfer function. From here I can calculate the say this is the input and this is the output, so I can calculate the gain. So we can calculate the gain, we can calculate the time constant. So approximating transfer servo motor, DC servo motor as a first order system, I can find out the transfer function of it too. So these are the references. You can go through the technical details. I think it is given in the first chapter itself, and a few other links where you can get details, technical details. So any doubt regarding my discussion of today regarding this DC servo motor characteristics? I'll share the PDF. I'll pass on the PDF of this PPT to Polomi, and Polomi, please share it with your friends. Any doubt? If you have any doubt, you can WhatsApp me, no problem. I will, if you have no doubt at this moment, I can close the session now.